Welcome back to Unit 6, which is continuing on in Chapter 10. We need the second part of Section 2. Today's target is that you'll be able to use Pascal's triangle / binomial theorem to expand binomial expressions, i.e. we're going to write them in standard form. Okay, we're going to go from a factored form to a standard form situation. So have this target ready to go for tomorrow, please. So Pascal's triangle. Pascal's triangle is just what it is. It looks like a triangle. We start at the top with a 1. That's what's always at the top. As we proceed, and we call this our row 0. Row 1 has 2 1s in it. Still not very interesting. Still hard to see a pattern. Row 2 is where things start to get a little different. We get a row of 1, 2, 1. Which is row 2. Row 3. I'm going to stop numbering him here. 1, 3, 3, 1. Can you predict what row 4 will be? 1, 4, 6, 4, 1. Are we seeing the pattern yet? Let's keep going. 1, 5, 10. Sorry about that. 1, 10, 5, 5. 1, 5, 10, 10, 5. 1, 1, 6, 15, 20, 15, 6, 1, 1, 7, 21, 35, 35, 21, 7, 1. If you can get the pattern, I'm going to have you pause this and see if you can predict what the next row will be. If you guessed 1, 8, 28, 56, 70, 56, 28, and 80, or 8 and 1, then you have the correct pattern. Okay? In a nutshell, the rows of Pascal's triangle can be found by adding the 2 values above them in each pattern, each row. So we got this 2 here in row 2 because 1 plus 1 is 2. And in row 3, 1 plus 2 is 3, 2 plus 1 is 3. In row 4, 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4. On the outside, in the left and the right, it's always 1s. So as you go down each row, you can develop as many rows as you want, because these numbers are getting larger and larger. We also notice that it's symmetrical. So if you drew an imaginary line, symmetry line down the middle of this Pascal's triangle, if I had to balance out a little better, you can see that values repeat. You kind of get to a maximum value in the middle, and then they fall back down, and they get smaller, and it's the same coefficients on the back side. So that's Pascal's triangle. I'm going to show you how we're going to use that here in a moment. Just so you know, if you put in your calculator 0, C, 0, that corresponds to this 1 right here. And if we put 1 combination 0, 1 combination 1, it relates to row 1, and so on and so forth. So this is also represented with combinations, and that's why it's in this chapter. Okay, so it's really that. Now, we don't really use the combinations, but that's how you can develop each of your rows. If you wanted to do row 25, you start with 25C1, 25C0, 25C1, 25C2, etc., 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 and put those in your calculator, and you can get whatever row you want without having to actually make the triangle. So we're going to use Pascal's triangle here to use it to actually expand a polynomial. So this goes with the binomial theorem. I'm not even going to go over the binomial theorem. It's something that goes along with the Pascal's triangle. I think Pascal's triangle is a little easier to understand. But in page 693 in your book, it does have the binomial theorem if you would like to read that and try it that way as well. Very similar to what we're going to be doing here. Expanding a binomial of some sort. So x plus y to the fourth. What that really means is x plus y times x plus y times x plus y times x plus y. And what we've had to do in the past is we foiled this over and over and over again. There is another way to do it. Okay? What we're going to do is we're going to use Pascal's triangle. So we're going to expand x plus y to the fourth. What row of Pascal's triangle do you think we're going to use? Well, whatever the degree is, or exponent, that's the row of Pascal's triangle that we're going to use. So we're going to write out Pascal's triangle first until we get to the row we want. Okay, and so there's row 4. That row is going to be the coefficients we're going to use for the expansion of our polynomial. So I'm going to write those out. 1, leave some space. 4, leave some space. 6, leave some space. 4, and 1. Okay, these are the coefficients of the polynomial. What's going to go next then? Well, what are the terms in our polynomial? Our terms are x and y. So we're going to put x and we're going to put y next to each other next to each of these coefficients. The final step, before we simplify, is assigning exponents to each of these. Here's how it works. So the first term, from the left to right, so in this case x, it's going to start out with whatever the degree is of the polynomial. In this case it's 4, because it's a fourth. We're raising it to the 4th power. So whatever row of Pascal's triangle we're in, whatever the degree is, it starts with 4. The other term starts at 0. And then what we do is for the first term, we go down by 1 degree, or 1 power. And for the second term, we increase it. And we do this all the way across. Go down by 1, go up by 1. Go down by 1, up by 1. Until they totally flip-flop, and by the last term, they are mirror images of each other. Okay, so that's what we're going to do. So when you add the 2 powers, or the degree of each of these together, we should add up to, in this case, 4. The last thing we do is we simplify these as much as we can. And some of them are going to be able to be simplified more than others. For this polynomial, we can see that y to the 0, well, that's just 1. So this is 1x to the 4th plus 4x to the 3rd times y plus 6x squared y squared plus 4x y cubed plus, once again, 1 times x to the 0 is 1 times y to the 4th. So we have just expanded x plus y to the 4th without doing any FOIL or any table method. Okay? We're going to try another one here, a little more complicated, but that gives you the idea. Whatever power it is, that's the row of Pascal's triangle we are going to use. So we're going to try one here that maybe is a little more tricky because we have other coefficients in front of each term, and with more numbers that are going to be involved, and there's a subtraction sign. So how is that going to work? First of all, we start out the same way. The 3 tells us we're going to be in row 3. So let's make row 3 of Pascal's triangle. 1, 2, 1, 1, 3, 3, 1. So these are the terms we're going to use for our coefficients. 1 plus 3 plus 3 plus 1. Now the terms are 5 and negative 2y. So 5, and we're going to put negative 2y in parentheses. So times 5, or times by, because that's a number, not a variable, so times negative 2y as well, times 5, times negative 2y, times 5, which you could put parentheses around it, but I haven't so far, so 5 times negative 2y. So those are the terms, they come right from A and B of the binomial. So now we're going to assign exponents, just like we did before. This starts at the power of 3, so 5 to the third, negative 2y to the 0, and then we just go down 1, up 1, down 1, up 1, down 1, up 1. At this point, we simplify each of these, and then we have our polynomial expanded. So 2y, negative 2y to the 0, that's just 1 again. And 1 times 5 to the third. Well, 5 to the third is 125. Over here, well, we have 3 times 5 squared is 25. Negative 2 to the 1 is negative 2 times y to the 1. We'll come back and simplify that again in the next step here. Show you what we did. We're going to distribute this to both terms as well. So I get 3 times 5 times negative 2 squared. Negative 2 times negative 2 is 4 times y squared. And over here, I'm going to get 1 times 5, 0 is 1. I get negative 2 to the third power, which is negative 8. And y to the third power is y to the third power. So a lot of you might just do these all at once instead of writing this out, but I'm doing this to kind of show you where all these coefficients are going to come from. So I end up with 125 plus, well, let's see, is it going to be plus? 3 times 25 times negative 2 is negative 150y. And then we have 3 times 5 times 4, that's going to be a positive. They're all positives there. That's 60 and y squared. And then a negative 8y to the third. I would be okay with it for this one, but if you wanted to be prim and proper, we would flip this around and put it in standard form. And we get this as the expansion. Negative 8y cubed plus 60y squared minus 150y plus 125. So that's a little more complicated way problem, but same process. Okay, here's another one. This one is this is one that you'll see more likely on the ACT. That's why I'm going to specifically do this one. Instead of having you expand an entire polynomial like this, they're going to ask you to find the coefficient of one of the terms. So you're really going to do the same process. It's just you don't have to have as much. There's a stopping point. You don't have to get the whole problem expanded. You can stop at a certain point. I'm going to show you how we're going to do this. But first, well, we need to determine what row we're in. We're in row 7. So in row 7, 1, 1, 1, 2, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 5, 1, 6, 15, 20, 15, 6, 1. And row 7, there's a lot of terms in row 7, aren't there? Okay. 1, 7, and 1. So we're going to expand this with using these as our coefficients. You'll see it's not as bad as it looks, I promise. Seven plus 1 plus 35 plus 35. We're going to continue this on down below. Plus 21 plus 7 plus 4. Okay, so I told you that this one, there is a way that it turns out to be a little easier. Okay, you'll see what I mean here in a minute. So our terms are x and negative 3. X, negative 3, 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 x, negative 3. So we're doing the same thing we've done in the other problems. You'll see that, you'll see that one. Now, remember, we wanted the coefficient of x to the 5th. So as you go through, tell me when I can stop on that, obviously. But think of it in your head. When can you stop going on? So we said 7 and 0. Go down 1, that's 6. 1, go down 1, 5, 2, 4, I mean, I'm going to keep going all the way through. Some of you may say, what is he doing? Why is he going? Talk about that in 1 minute. 2, 5, 1, 6, 0, 7. Now, if I was to expand the whole thing, I'd have to worry about every single one of these terms. But instead I wanted the coefficient of x to the 5th. X to the 5th is going to be this term. I don't have to simplify the rest of this. So I can just take that term out and simplify it. And that'll give me the coefficient. So I get 21 times 3 squared, or 21 times 9 times x to the 5th. 21 times 9 is 189. So that's what that term would be instead of wanting the coefficient. Well, the coefficient of x to the 5th is 189. Our answer is 189. So we follow the same process. This is what they would ask you on the ACT if they wanted the coefficient of a certain term. They'd want you to go through this process, but you'd only have to concentrate on one term. And if you're thinking about it, and you know you're setting it up, the 5th term, well, 7, 6, 5, and you know that's the 3rd one in, that even shortens it up even more. So, that's using Pascal's triangle to expand a binomial. Please have your notes ready for tomorrow, as we'll have the assignment in class. We'll see you then.